Well, it's about time we learn a little bit more physics, and this time the topic is friction. Well, we all know what friction is. It's when things rub together. When you rub your hands together to get them warm in the wintertime, that's friction. Any of you who are into scouting, maybe you learned how to rub sticks together to generate some heat and maybe even start a fire. That's friction. But the question is, what is friction? Well, I'm going to try to answer that a little bit today. If you look at your feet rubbing against the ground, it's friction that allows you to walk. No friction, no walking. Think about it this way. You push backwards on the surface of the ground, or in this case, a floor, and by Newton's third law, that means, let's see, the floor has to push forward on your foot. So it's actually the floor pushing you forward when you're walking. Isn't that weird? You don't think about it that way, do you? Same thing happens with an automobile tire. When the tire spins, in this case counterclockwise, that pushes backwards on the ground. The ground responds by pushing forward on the car, Newton's third law. Every time an object exerts a force on a second object, then the second object exerts an equal and opposite force on the first. But once again, we're talking about the effects of friction, not what friction actually is. Let's take a look at it. Let's suppose we have a block on top of a table. If you look microscopically at the surfaces of the two, as we've done here, you can see that under a microscope, the surfaces, which might appear to be smooth to your eye, are actually quite rough. They have little nooks and crannies, kind of like an English muffin. And if you push down on the top of the block and the table pushes back up with its equal and opposite force, those little teeth will kind of lock together with each other, and it makes it harder for you to be able to move the object horizontally. Furthermore, if you push down when they're not moving, they have a chance to really sink into each other. That's called static friction. And that's really much more difficult to overcome. Once you get it moving, it's easier to keep it moving because now they're kind of bumping across each other. So that's the basic idea of friction. Now, if you're thinking, well, didn't you tell us about 4 fundamental forces? Which one of these is this? Well, this one would be the electromagnetic force. Think about it. The reason that objects don't simply pass right through each other is because their electron shells, which have negative charge, repel the electron shells of other objects. And so it's those outer electron shells, the electromagnetic force between them, that causes friction. Okay? Friction is a contact force between objects that resists their relative motion. When you put your hands together, you try to move them, it's the friction that causes you to have to exert more sideways force to get them to move. And it's a contact force when we speak of it macroscopically. It's only at the microscopic level that it becomes an electromagnetic force. F sub s is the symbol that we're going to use for what's called static friction. That's the friction that exists between objects that are not moving relative to each other. So for example, in that previous picture where we had the object on the table, the box, if I tilt the table up, the box won't immediately start moving because it's the static friction, microscopically the little fingers holding onto each other, that keep it from moving. On the other hand, kinetic friction, F sub k, or sometimes called sliding friction, is when objects are already moving, and it's the friction that exists in that case, and that's the friction that can generate some heat also. There's a third kind of friction called rolling friction that we're not going to discuss here, but it has to do with, for example, a tire rolling along the road and the friction that's generated there. We're going to deal primarily with static friction and kinetic friction. I mentioned math earlier. Don't worry, it's coming up. I know you're very, very excited about that. Frictional force is proportional to normal force. Now that's a statement that probably, if you haven't seen this before, has no meaning to you. So I'm going to try to explain. Let's suppose we have someone's hands pushing a block against a wall. Okay? Yes, I created that little picture all by myself. What I want you to think about is this. There's already force on the block called gravity pulling down on it. If the hands weren't there, that block would be falling. In fact, even with the hands there, the block might be falling. The hands have to exert a push against the block, and that pushes the block against the wall. By Newton's third law, the wall responds by pushing back against the block. And so we have the applied force here by the hands and the normal force exerted here by the wall. That normal force causes those little nooks and crannies to sink into each other, and that increases the amount of frictional force. Which way would the frictional force be pointed? Well, it would oppose the attempted motion of the block. The block wants to fall due to gravity, and so the frictional force, and I'll place the frictional force right there on the surface between the block and the wall, is going to oppose that attempted motion. Now, if it's actually not moving, those two forces are going to have to be equal to each other. Otherwise, it would be accelerating. Make sense? I knew it would. So, as I mentioned, frictional force is proportional to normal force. That can be translated into an equation. In the case of kinetic friction, we would say that the kinetic frictional force is equal to some number times the normal force. That's what we mean by proportional. Where mu, that's the Greek letter mu, spelled M-U, okay? Think of what kittens say, not what cows say. It's not moo, it's mu, okay? Where mu sub k is the coefficient of kinetic friction. It's a coefficient of proportionality, a constant of proportionality. And so that's what we mean when we say the frictional force is proportional to the normal force. On the other hand, if we're talking about static friction, the normal force can get really big without changing the frictional force. And so we'll say that the frictional force is less than or equal to the coefficient of static friction times the normal force. Think about those hands pushing the block. Once the block is stopped, the hands can push harder and harder, so the normal force gets bigger and bigger, but the frictional force still stays the same as gravity. So that's the reason for the inequality there. Got that? All right. Something worth noting. Frictional force is in newtons or pounds. Normal force is also in newtons or pounds, which means the coefficient of friction does not have a unit. It's completely dimensionless. What does coefficient of friction depend on? Well, we're kind of simplifying the process here a lot, but it depends on things like what are the two materials. The coefficient of friction between a rubber eraser and another rubber eraser is going to be a very, very high number. And by a high number, I mean 1, okay? Whereas the coefficient of friction between, say, a wet ice cube and a hard linoleum floor is going to be very small, maybe 0.05. And that's what gives you low friction for wet ice and high friction for rubber. Maybe that's why rubber is called rubber, because it rubs, okay? So let's try a quick example. The coefficient of static friction between a 20 kilogram box and the horizontal floor is 0.55. That's actually moderately high. A rope is attached to the box and is pulled horizontally, obviously to the right. How much force must be applied to get the box to move? So we're talking about static friction since it's not moving, and that's why it's important to know the coefficient of static friction. By the way, the coefficient of kinetic friction would likely be a smaller number because, as mentioned earlier, it's harder to get something to move than it is to keep it moving. So what do? Why, that's right. We draw a free body diagram of the box. So there's our box, and let's apply some forces to it. Well, we have that force to the right. That's going to be the force exerted by the rope. We have that force to the left. That's going to be the frictional force. What else is relevant? Well, we have the weight of the box pulling down, and we have the normal force pushing up from the table, or the floor in this case. The mass of the box is 20 kilograms, and the coefficient of friction is 0.55. Let's see if we can work the problem from there. Now we're going to need a few more things on our diagram to make this a really good free body diagram. One of them is we have to choose positive directions. I'm going to choose up and to the right as our positive directions, and we'll even call them X. Yes, believe it or not, that's an X. And Y. And we need labels on these forces. Since this is the applied force from the rope, I'll just call it with a big capital F. Since this is the frictional force from the table to the box, we'll call that lowercase f. Since this is the weight, we'll call that mg. And since this is the normal force, we'll call that N. Okay? Now, can we compute any of these? Well, we know the mass. mg is self-defining on how to compute it. It's going to be 20 times 9.8, which is 196 newtons. And then what else do we have? Well, since the sum of the forces in the y direction is 0, remember it's in equilibrium, it's not moving in the vertical direction at all, then we could write that these two forces are equal to each other. We could go through the step of actually following the rule and writing N, which is a positive force, note the arrowhead, minus 196, y minus, as we're adding a negative, note the arrowhead and the positive direction, is equal to 0. So in fact, we get that the normal force is 196 newtons. So what do we do with that? Well, over here is where we have to remember that friction is fun. What do I mean by that? Well, our formula is that frictional force is mu, the coefficient of friction, times the normal force. Doesn't it look like it spells the word fun? The only problem with that is mu is the Greek version of the letter M, not the Greek version of the letter U. So this would actually say friction is and that doesn't really sound right. But if we plug some numbers in here, it's going to look right. So we have 0.55 times 196. And so we get that that frictional force is 107.8 newtons. And I'll put that right up here on the diagram. But now the question is, how much does this force have to be to just get the box to move? Well, remember, this is a static friction. That's a coefficient of static friction. This is a static frictional force. If we can overcome static friction, just barely, the box will begin to move. So essentially, we're using Newton's first law again. In this case, the sum of the forces in the x direction is 0. Well, technically is going to be slightly greater than 0. So let's make it greater than 0. And so let's see, the sum of the forces, that would be F minus 107.8 is greater than 0. Y minus, again, look at the positive x direction and look at the arrowheads. And so we get that that force has to be greater than 107.8 newtons. Now that is too many significant figures for the information that I've given to you. Maybe we'll just round it to 108 newtons. But as long as the force is greater than 108 newtons, then that means it's going to overcome static friction and the box begins to move. Make sense? Okay. We're going to pause there. In fact, I'm going to end the video there with that example. We're going to do an interesting kinetic friction example in the next video. I think you're going to like that one a lot. See you then.